Bonjour à tous, bonjour à toutes. Je suis Guylaine Baudry, la doyenne des bibliothèques et titulaire de la chaire Trenholm, et j'ai le grand plaisir de vous accueillir à la conférence Mossman de 2023. I am delighted to welcome you all to tonight's Elizabeth B. McNab Lecture in the History of Science, presented by the Mossman Endowment and supported by the Friends of McGill University, Inc. We are live from beautiful Morris Hall on McGill campus today. I would like to take this time to recognize that McGill University is on land which has long served as a site of meeting and exchange amongst indigenous peoples, including the Haudenosaunee and Anishinaabe nations. We acknowledge and thank the diverse indigenous peoples whose presence marks this territory on which peoples of the world now gather. May we dedicate ourselves to moving forward in the spirit of partnership, collaboration, and reconciliation as we learn together and contemplate the possibilities that lay ahead. The legacy of Dr. Donald Mossman lives on today in the lecture series he founded to further the understanding of science and in the collection of donated books on the history of science and ideas. Dr. Mossman was born in Montreal in 1898. He studied chemistry at McGill in the 20s. Though he went on to graduate studies elsewhere and subsequently taught chemistry at Hunter College in New York, his allegiance lay with McGill, his first alma mater. In 1974, he and his wife, Dorothy Mossman, donated their collection to McGill. The 1,700 books can be found in the Schulich Library of Physical Sciences, Life Sciences, and Engineering. Their generosity did not stop there. In 1982, a donation was made by the Mossmans to maintain and further develop the Mossman collection and to encourage teaching and research in the history of science and of ideas. With this endowment and a later bequest, Dr. Mossman was established two named lectures in honor of his two great friends, also McGillians, Elizabeth B. McNab and D. Lorne Gales. Tonight's lecture is the Elizabeth B. McNab Lecture in the History of Science. Elizabeth B. McNab's connection to McGill spanned 40 years. She was a graduate of McGill. She earned her BA in 1941 and had a distinguished career at McGill, becoming the first woman to hold the position of Director of Annual Giving at the Canadian University, and later the first woman to become Head of University Development. Her activities in alumni relations and fundraising took her to New York, where she met and became friends with Dr. Mossman. Upon Dr. Mossman's retirement, Miss McNabb assisted him in the transfer of his personal library to McGill and in the establishment of an endowment to maintain and add to this collection. Elizabeth B. McNab passed away on December 31st, 2006. We pay homage to her outstanding contributions here tonight. Dr. Mossman once said, quote, "The study of the history of science alone may suffer a degree of cultural barrenness similar to that of many other scholarly studies if no attempt is made to relate it to the climate of opinion in other disciplines existing during the period studied. For there can be no doubt that religious, philosophic, political beliefs, and social attitudes have all frequently affected one another, and that there have been mutual influences between these and the progress of science. This view strongly suggests the wisdom of a rather eclectic approach to the history of science. This we deem highly desirable." End of quote. I have no doubt that today's lecture will honor his vision for interdisciplinarity. Bob McDonald has been bringing science to the public for more than 40 years. In addition to hosting Quirks and Quarks, the award-winning science program that is heard by 800,000 people each week, McDonald is also science correspondent for CBC TV's The National and host of the children's series Heads Up. He was also host of the CBC children's series Wonderstruck. He has written and hosted numerous television documentaries and more than 100 educational videos in Canada and the United States. As a writer, he has authored 6 best-selling science books, including the 2022 Canadian bestseller, The Future is Now, Solving the Climate Crisis with Current Technology. McDonald has also been honored for his outstanding contribution to the promotion of science within Canada. He holds 12 honorary doctorates from Canadian universities and 2 honorary diplomas from Canadian colleges, and in 2015, Asteroid 332324 was officially named Bob McDonald in his honor. He is an officer of the Order of Canada and a recipient of the Queen's Jubilee Medal. Please join me in welcoming Bob to the podium. Thank you.
Merci. Merci, Madame Dean. Bonsoir, Mesdames et Messieurs. Ma mère s'appelle Elena Leblanc, Acadian French from St. John, New Brunswick. So I have French roots, and it's wonderful to be back here at McGill. I've done many stories out of this fine university over the years, and it's wonderful to be back. Do you still have a combustion lab here where they just blow stuff up? That was one of my favorite parts. I don't know if they still do that. That was great. And it's been wonderful. I also heard, well, I have a great job. I have a great job. I talk to smart people for a living. Every week on Quirks and Quarks, scientists from all over the world tell me their stories. And it doesn't matter what it is, whether it's some new galaxy out at the edge of the universe or a new black hole or the sex life of some insect, I don't care. It's all new. It's all new. And that's what science is all about, and that's why I'm so fascinated in it and why I've been doing it for so long as a journalist, because it's one of the last institutions we have that's trying to seek the truth. The truth. How does the universe work? That's all that science does. And it's a very organized way of doing that. And organizations that seek the truth seem to be becoming fewer and fewer in number these days. We're in an age of misinformation, an age of denial and things like that. And it's no more important for us to be literate in science than right now, because we're facing some very serious issues with things like climate change, with things like population, biodiversity loss. All of these things that are happening all have scientific principles behind them. And that's why I did this book. I've been reporting on science and the environment for a very long time. How long? Let me show you. Ever since I looked like this. Come on. I notice a lot of you here dye your hair gray, just like I do. It's a little shorter now, that's all, no difference. This is 1978, when I was working at the Ontario Science Centre in Toronto, and it was also my first job at the CBC. I was invited to write a 1-hour documentary for the radio program Ideas on climate change. 1978. And back then there was a debate in the scientific community about which way the climate was going to go. The geologists who looked really far back in time, they were saying, well, you know, we've had 4 or 5 ice ages. And between those ice ages, there were warm periods that lasted about 10,000 years each. Well, it's been 12,000 years since the last ice age. We're overdue for another cooling period. But then the climatologists were chiming in, and they were saying, nah, there's a new ingredient. Greenhouse gases, carbon dioxide, methane, water vapor, they're going to increase the temperature. So there was a debate. They didn't know which way it would go. That was 1978. Well, we know who won the debate. And as a journalist, it's been very frustrating for me to watch all of the predictions that the scientists were making back in the 70s come true. They predicted that the Earth would get warmer, especially in the Arctic, because we're losing ice, and ice reflects sunlight, but dark seawater doesn't. The ice disappears. They were predicting it would be gone in 2050. It's already almost all gone now during the summer. Last summer, I took a cruise in the Arctic. There are cruise ships going through there now. It's unbelievable. So they predicted that. That came true. They predicted that storms would become more stronger, and we're seeing that. Look what happened in Port aux Basques last year in Newfoundland. The storms are going farther north because the oceans are warmer. There's more fuel for them. They predicted droughts. This is Lake Mead in the United States behind the Hoover Dam, drying up because the states have been in drought for about the last 8 or 9 years, and water levels are a crucial issue. Now, they had a lot of rain and snow this year, 1 year, which is good, but it's still not enough. They predicted droughts. They predicted the storms. And where I now live in British Columbia. This is an aerial photograph of British Columbia, southern BC. You can hardly see it because it's under smoke. We had wildfires there 2 summers ago, and I was driving through this stuff on my motorcycle, and I had to turn back because I think I inhaled an entire tree in smoke. It was burning my lungs and burning my eyes. It was terrible. So they predicted wildfires. So we've watched all of these things come true. And meanwhile, I've also watched our governments come together in these United Nations conferences. In fact, I was at the very first one. Rio 92, the Earth Summit, the world's first Earth Summit. And all the world leaders got together, prime ministers and presidents, kings. They came together in Rio and they said, yes, climate is an issue, biodiversity is an issue. We have to take care of both of them. Then everyone went back to their countries and nothing happened. We've had 26 of these meetings over the last 40 years, 26 of them. And the bottom line is our emissions are still rising. There has been some work, there has been some progress, but it's still rising. The young people are not happy about this. And I'm sure a lot of the students in this university are afraid of their own future because it's their future we're talking about. So this kind of gets depressing. But as I say, no matter all of these things, the temperature's still going up. You've seen graphs like this before. It's going up. We have hard evidence from observatories in Hawaii, from satellite work, from ice cores, from tree rings, from the geological record. We know that we're now living in unusual times. And it's not so much that the Earth is really warm right now. In fact, when the dinosaurs were here, it was warmer than it is now. But it's the rate of change. We're changing it so quickly. Climate change in the past took hundreds of years or thousands of years to change. Now we're doing it in decades. So that's the issue. So this was all getting me down. I was starting to get depressed because all the news coming out of the environment is bad. It's all bad news, man. This is getting me down. I also was not expecting during this whole time that not only would the scientists not be listened to, but there would be a very well-organized campaign of misinformation telling us that climate change was not real, attacking the science, picking specific information, and putting it together to make it look like we're getting cooler, things like that. I was not expecting that. And we now know that some of that was funded by ExxonMobil. So these are all things that I didn't think would happen, but did, and I was starting to get down about it, so that's why I decided to write a book. I thought, we've been spending so much time pointing out the problems. What are the solutions? Where's all that green energy, all that green technology stuff? And it was to my absolute delight that when I did the research on the book, that I found out that all the technology we need to go green already exists. We don't need to invent anything new to go green. It's already there. We know how to capture the energy of the sun, the energy of the wind, the geothermal energy that bubbles out of the ground, tidal energy if we want, wave energy. It literally grows on trees. Canada's good at nuclear energy. We've got to have a rethink of nuclear energy. It's all there. Energy, there's no energy shortage. In fact, there's as much energy falling out of the sky every day in 1 hour that all of us use in a year. 1 hour. It's amazing. All we need to do is gather it up. Well, so why haven't we? If all that stuff's out there, why haven't we? What's been going on? Well, there's a lot of reasons. But one of them, the big elephant in the room, is this stuff. It is remarkably convenient. Oil is amazing. Oil is amazing stuff. It has driven the whole industrial revolution, fossil fuels. No wonder. It contains so much energy in such a small space. You can carry it around in tanks. You can use it when you want. And it's incredibly energy dense. Only nuclear fuel is more dense than fossil fuels. And you think about it, all you need to do is dig it out of the ground and light a match. And it goes, I mean, think about coal. Coal is a rock that burns. Just take a rock, light a match, it burns. That's amazing. We don't have to do anything to it. And that's what we've been doing all along, is just lighting matches and burning it. And that's been one of the problems. But I'll get to that in a second. So how much energy does oil actually contain? Well, there's a metric unit called the joule. And if you take one standard barrel of oil, it contains about 6.3 billion joules. Now, that's hard to get your head around. Let me give you a demonstration. A joule is 1 kilo raised 1 meter. Now, this is more than a kilo, so about half of this. But suppose this is a kilo. If I go from here to there, I just put out 1 joule of work. 1 kilo raised 1 meter. So if I do this 6.3 billion times, that's how much energy is in a barrel of oil. It's huge. It's huge. Now, it's, again, these numbers are so big, it's hard to get your head around. So somebody did another unit of measurement rather than just joules. They used the Great Pyramids of Egypt. Somebody actually calculated how many joules it took to build the pyramids by simply adding up the mass of all the stones and how high they had to be lifted. And the number they came up with to build the pyramids is 2.4 trillion joules. Okay? Again, these numbers are getting ridiculous. But how much oil would that represent? How much oil would it take to build the pyramids? It turns out 400 barrels. That's it. One oil well can pump 400 barrels in one day. 400 barrels of oil would build the pyramids. It took the ancient Egyptians 20 years to do it once, and we could do it with one oil well in one day, 400 barrels. And when you look at all the energy that we burn worldwide in all of its forms, and you put it all together in pyramids, it works out that every year we burn 2 million pyramids worth of energy. 2 million pyramids a year. That's unbelievable. And we take it for granted, you know. Flip a switch, the lights come on. They're always there. Although I understand some people are having trouble with your subway system tonight. It broke down. There you go, right? As soon as it's gone, you know, what happened? How come it doesn't work? Oh my God, we lost some electricity. So we're spoiled. We're spoiled with this stuff, and we're not going to let it go. And let me be very clear. I don't want to make an enemy out of the oil industry. They're not the enemy. Because if you do that, you say, ooh, the evil oil empire on one side and the good tree huggers on the other side, you've polarized it. And as soon as you do that, both sides dig in their heels and nothing happens. What we need here is a little cooperation. A little cooperation. How could we get energy out of oil without all of those emissions that come out of it? Well, maybe there's a different way to burn the oil. You see, we call oil a hydrocarbon because it's a chain of carbons with a bunch of hydrogen attached to it. I think of it like a string of Christmas lights. The oil, the carbon is the string, the hydrogen are the bulbs. And when you plug in the lights, it's the bulbs that come on, right? Well, when you burn oil, it's the hydrogen that's coming off, giving you all the energy. The carbon stays behind. The carbon wants to combine with other things like oxygen, carbon dioxide. Great, carbon monoxide. If there's sulfur there, sulfur dioxide. And all these things are just thrown out into the air. We throw that away. It's only the hydrogen. So, what if we just took the hydrogen out, leave the oil in the ground? Well, there's a company in Saskatchewan doing that. It's a company called Proton Technologies, and it's a very clever technique. What they do, they have 2 oil wells, and these are abandoned oil wells. They've already had most of the oil pumped out, but there's still a lot underground. Down one of the wells, They put high-pressure steam. And there's a process called reforming, where steam will combine with the oil and pull the hydrogen out. And then the hydrogen bubbles up the other well. And you can use hydrogen as your fuel. And hydrogen's a good fuel because when you burn it, all it does is combine with oxygen, and you get H2O, water. And by the way, Dr. Schwarcz, you're going to hear Joe Schwarcz in just a second. You corrected me one time. You probably don't know this. We were speaking at a conference. It was an environmental conference. And I was doing a thing on water. And I held a glass up of water, and I said, let's have a toast to dihydrous oxide. 2 hydrogen, 1 oxygen. Joe came up to me later, he says, Bob, it's dihydrous monoxide. There's only 1 oxygen. So thank you. So every time I do that now, I think of you. Of course, this is why we need the scientists. You see, the difference between the scientist and the journalist. I'm not a scientist. I'm a journalist. He's a scientist. And we need both. He's also a journalist. In fact, there was a scientist, a journalist, and a politician who were out fishing. Wasn't a lot happening. And a frog stuck its head out of the water, looked at the scientist and said, I have a PhD, I could be your thesis advisor. And the scientist said, I already have a thesis advisor. So the frog looked at the politician and said, I have a PhD, I could be your science advisor. And the politician says, I'm not interested in science. The journalist reached down, grabbed the frog, and put it in his pocket. And the scientist said, why do you need a PhD? The journalist said, I don't. But a talking frog is a big story. That's how we work. But we need each other, right? We need each other. Okay, so this is one way, just one way of getting energy out of oil. The carbon stays in the ground. That's the point. The carbon stays in the ground. It's only the hydrogen that comes up. And we know how to turn hydrogen into fuel. There are prototype cars. Toyota already makes one called the Mira, and it's a fuel cell car. So it's basically an electric car. It has an electric motor driving the wheels, but the fuel cell produces electricity. And a fuel cell is sort of like a battery, except instead of having all your chemicals in one brick, you got a fuel tank with hydrogen, and it mixes with oxygen, and that's what gives you the electricity. And again, the only thing that comes out the tailpipe is water. So it's a very, very clean fuel, but you have to make it. You don't dig hydrogen out of the ground. You got to make it. So it does take a little energy. Airbus Industries is looking at this, and they're talking about building hydrogen hybrid airplanes. They're building a commuter plane that's like our Canadian-built Dash 8 with engines that run both on hydrogen and electricity. They're also building a commuter jet, like our Bombardier jet that we have, that Airbus bought, but it's going to run on hydrogen and on electricity. And they're talking about a futuristic called a blended wing, where the wing and the body are both lifting bodies running on hydrogen. Now, there's only one issue in the airline industry. Jet engines take up a lot of fuel. And right now, that fuel is in the wings. Hydrogen's a great fuel, but it takes up more space because it's a gas, and it's just so they need bigger tanks. So rather than putting bigger wings on, they're going to have tanks within the fuselage where you sit. So how would you feel getting on an airplane knowing there's a big tank of pure hydrogen right behind you? I know what you're thinking. I know what you're thinking. You know, it's too bad that the Hindenburg gave hydrogen such a bad reputation, because a whole bunch of people survived this. A whole bunch of people survived. I think it was more than 90 people survived this crash, believe it or not. Why? Because the hydrogen fire went up. Hydrogen is lighter than air. And you can see it right in this photograph. The flames go up. And as the ship settled to the ground, losing its lift, people just jumped out windows and they ran out from under the fire. The people who died in the Hindenburg were killed by the collapsing wreckage and diesel fuel that burned till the next morning for the engines. It was a diesel fuel, because diesel fuel is heavier than air. That's why fire trucks show up at car accidents on the highway. They're worried that the gas tank got punctured, the gasoline would leak and go underneath the car and turn it into a barbecue. Gasoline. So when you think about it, gasoline is actually more dangerous than hydrogen. If you get a leak of hydrogen, it just goes up. You get a leak of gas, it goes down. So these airplanes will have vents at the top. If there's a leak, it goes up. So that's the thing. We got to get over the hydrogen Hindenburg thought. let's get the Hindenburg out of our mind. It's too bad that happened. All right, so that's oil. That's another way to deal with oil so that the oil companies can still give us energy. It'll just be in a different form. So when you go to a gas station to fill up with hydrogen fuel, it'll still say Shell or Exxon or Petro-Canada or whatever, but it'll be a different fuel. And we already have the technology to do that. Okay, cars themselves are becoming more electric. We're seeing more electrics on the road. How many people here have an electric car? 1, 2, 3, 4, 5. Yep. Wow, more. They're coming. They're coming, right? And if you have an electric car, you really like it, right? Because it goes like crazy. I thought it was very brave of Ford a few years ago to take their iconic muscle car, the Mustang, which has a truck engine in it. A truck engine in a car that puts out, what, 600 horsepower, something like that? And they took that brand and they turned it into an electric crossover. You can still get the 600 muscle car if you like, but they turned it into an electric car. That's very interesting. I don't know what the performance is like, but the comparison of these two cars in terms of the energy that they use, if you take the Mustang, at best, it's 20% efficient. All gas engines. And the gas engine, by the way, has been around a long time, more than 150 years old. The 4-cycle internal combustion engine that's been running all of our cars. But they're only about 20% efficient. That means of all the energy that's in the gasoline, which is a lot, only 20% of it actually turns the wheels. 80% is lost as waste heat. That's how those engines work. You got to keep taking heat away or they won't run. So the heat goes out the tailpipe, the heat goes out the radiator that's at the front. 80% we throw away. And the only reason we've gotten away with that for so long is because gasoline is so energy dense. There's so much fuel. You can afford to throw 80% away and still drive at 130 kilometers an hour from here to Toronto. It's amazing. Well, we can't do that because one thing, those carbon emissions, the average car produces its own weight in carbon every year. Its own weight in carbon, and we're just blowing that stuff up into the atmosphere. That's unbelievable. So think about all the cars on the road. Just throw them up into the sky. That's what we're doing every year, the mass of all these cars. Another way to think about it. Suppose you're going to go fill up. What's the price of gas here in Quebec right now? What? $1.79? Oh, okay. It's almost the same as it is in British Columbia. $1.79. So a fill-up now is approaching $100, right? Okay. Let's suppose you're going for a $100 fill-up. I never thought I'd say that. When I was a kid, boy, this is how old I am. Gasoline was 25 cents a gallon. I'm not kidding. I'm not making that up. That's 4 liters for 25 cents. Anyway, okay, $100 a gallon. How would you feel if you go to the gas station to fill up, you take the nozzle out of the pump, you put it in your car, and you start pumping away, but you stop at, what's 20% of 100? 20, right? $20. Okay, so you stop at, there are 3 kinds of mathematicians. Those who can count and those who can't. Just let that sink in for a second. Okay, so you're at $20 and you stop. Take the nozzle out of your car and point it into the air and pump $80 into the sky. You'd probably be arrested for polluting, for wasting gas. But that's exactly what we do. We're only using $20 out of that 100 to turn the wheels. That's nuts. Let's get over that. An electric car is 80% efficient. Almost all the energy you put into the motor turns it into motion. And there's only one moving part in a motor. A gas engine has about 200 moving parts, and a lot of them are bouncing up and down. So the electric car makes a whole lot more sense. Now, people will say, oh yeah, what about the mining of the lithium and all of that? Yep, that's an issue. But compared to what we're doing, drilling for gas and oil and fossil fuels now, it's minor. And the other thing is, once a battery is made and put in the car, that's it for the life of the car. That's it. You don't have to fill it up with any fossil fuels. Whereas gasoline, you got to keep pouring it through your car all the time. So it's a different game altogether. Battery technology, there's a huge amount of energy going into battery technology right now to develop better ones. Toyota's working on solid state batteries that are really thin. There are aluminum air batteries. There's sulfur batteries. I saw one battery, it's a piece of iron, and all it does is rust, and you get electricity out of it. So there's all kinds of chemistry, because people know that right now, if you can come up with a lightweight battery that contains as much energy as a tank of gas, and you can fill it as fast as a tank of gas, you're going to be rich. So you watch. There's a lot of effort into that right now. So that's cars. Okay, let's move on to the energy that falls out of the sky for free, the solar energy. You're probably familiar. Anybody have solar panels on their roof here at their home? Couple? I met a guy just recently. He said, we put solar panels on our house, and I've never had so much electricity. Don't know what to do with it. You can actually sell it back to the grid if you have enough. We also see these giant solar farms that take up a lot of land. People argue, yeah, but that land could be growing food. It's covering the land. Well, there is agrivoltaics, where you put spaces between the solar panels and plant crops in lines. So you have both the sun, well, the sun's doing it all, but the technology and the growth can happen at once. But there's another way to gather sunlight. Instead of just covering a huge field that might cover like hundreds of square kilometers in some countries, like India. India did an interesting experiment because agriculture is very important to them. They didn't want to cover all the land. How about covering canals? India is irrigated with all these canals. They have thousands of kilometers of canals. So they put solar panels over top. And what they're finding is that now you get a long area for the solar panels, but the solar panels shade the water. So you don't get as much evaporation, and you also don't get as much algae growth. And the water cools the solar panels. Turns out they work better if they're a little cool. So it's a win-win situation. Find other places for solar panels. California is looking at the same idea because there are a lot of irrigation canals there. And here's another idea that I got very excited about. Besides these silicon dark panels that we're all familiar with, there's another kind of solar material. There's a class of materials called perovskites. And these are crystals that you can print into very, very thin films. And in some cases, you can see through them, which seems kind of counterintuitive. If sunlight goes through it, how are you capturing energy? Well, these can be tuned to capture wavelengths of light that we don't see. In this case, it's ultraviolet. We don't see ultraviolet light. Some moths do, but we don't. So the visible light can go through, the ultraviolet can be turned into electricity. So where are you going to put them? Well, you think about all of the windows that are in the downtown buildings in our cities that face south. That's a huge area. You could put perovskite film on all of those windows to not only cut down some of the sunlight coming in, because you can't tint them, but they're also contributing to the power of the building. They're talking about perovskite paint. I love this. All you have to do is paint your house, and it's solar. Paint your house. They talk about indoor paint. Like, imagine if these walls were painted with perovskite materials. Some of the light that's coming from these lights would be absorbed by the walls and turned back into electricity. Recycling light. I love that. Recycling light. They're talking about perovskite clothing. You want to charge your phone? Put it on your shirt. Go out on a sunny day. Your shirt can charge your phone. So this is the thing with solar. You're going to see it. Well, actually, you won't. You won't see it. It'll be incorporated into the architecture of buildings and fabrics. That's exciting. And that's the future. Our energy is going to come from so many different sources, not just one nuclear plant or one hydroelectric dam or one coal-fired generating station. It'll be from all kinds of sources, including your own home. Let's move on to wind. We've been capturing wind for centuries, sailing up and down the Nile, the ancient Egyptians, the Romans around the Mediterranean. We crossed oceans on wind power. The Dutch built their whole country on wind power. And when North America was first settled from Europeans and they moved west out to the hinterland out there was no electricity, so they had the ubiquitous farm windmill, which both pumped water for irrigation, and at night they ran little turbine generators to keep the lights on in the house. So we've been capturing wind for a long, long time. But this form with the multi-blades is not the most efficient. It turned out that after many years, the three-bladed propeller design is the most efficient. It's balanced with only 3 blades, and you can make them really, really long. And they took a cue from the airline industry and propeller industry, and they're actually shaped like wings now. So they fly. They actually fly through the air. They develop lift. So they're very, very efficient. They're also big. They're getting larger. Size matters in both solar and wind. And it's because of that formula. Remember the formula you had to use in school, learn in school? Pi r squared, the area of a circle. There was a kindergarten school, a primary school, and they were having a parents' night. And the principal came out and said, we've got our smartest student in kindergarten who's going to tell us what she knows. So the little girl goes up on stage and says, pi r squared. Everybody goes, wow, that's amazing for kindergarten. Then the teacher comes out and says, no, that's not right. Pi r round, cake r square. Where was I? Oh yeah, in wind technology, the blade is the r. The blade is the radius of a circle. So if you make your blade just a little bit longer, you square the area. So make it twice as long, you get 4 times the area. So that's why these things are getting so big, is that you get all the surface area. The largest at the time I wrote the book was 14 megawatts. One windmill, one of these, can power 16,000 homes. One. A single rotation of the blade can produce enough electricity to power a home for 2 days. One windmill can do that. And to give you a sense of scale, this is our Parliament buildings in Ottawa for scale. That's how big it is. They're huge. They're huge, twice the height of Niagara Falls, almost the height of the Eiffel Tower. They're gigantic. So this is the future of wind. They're just going to get really, really big. But we won't see them on land. We'll see them offshore. Europe is already doing this. The US is talking about doing it in the Atlantic. Canada's, well, we've got some wind in the west and a little bit here in Kingston and Lake Ontario, but we could do more. We could do more. We're such a large country. We've got huge wind resources here. We could be doing more than we are. If you take the same technology and you make it smaller, you can put it underwater and you can capture the motion of the tides. And there was a project, a proposal to put water turbines in the St. Lawrence River because there's a constant current there. But I don't know if that ever came to, do you know, Joe, if that ever came to fruition? I don't think so. But it was a neat idea because the river's always flowing. So there's a lot of energy in water. And because water is so much denser than air, your turbines don't need to be so big. Although the problem is that when they're underwater, they'll gather all kinds of gunk, moss and slime and sludge and mussels and barnacles and everything. So you got to haul them up to clean them every once in a while, which is very expensive. So another alternative to capture the energy of the tides, in Scotland, they have this thing that looks like something Batman would drive. And it's just this big boat with these huge wings that can go down in the water and the big propellers spin to give you energy. And then when you need to clean them, you just raise them up and you can work on them on the surface. These things are being exported. You can tow them anywhere in the world where there's a good tidal flow. In Canada, we have a lot of tide on the East Coast in the Bay of Fundy. And where I live in British Columbia, I'm a sailor, and we have the Gulf Islands. And when the tide goes between islands, it speeds up. In fact, when I first moved there, I was out on my sailboat, beautiful day, I had all the sails up, cruising along, thinking, wow, this is really great. Then I looked at the shoreline, and it's doing this. I was going backwards because the tide was stronger than the wind. I thought, well, I guess we're going this way now. So there's a lot of energy in tide. And we know when the tides are going to be flowing down to the minute for the next 500 years. They're so predictable. And I have a story in my book about how I got caught in one of our strongest tidal currents in Canada, the reversing falls of St. John, New Brunswick. I went through that in my sailboat. Don't do that. So I have a bunch of personal stories in the book as well about how I've encountered the force of nature in many different ways. Okay, now a big complaint about the alternative energy is that the sun doesn't always shine, the wind doesn't always blow, and tides go slack twice a year. Alternative energy is variable. So how do we deal with that? Because we want energy 24/7. Well, one way is to store it. Like we have excess energy at night that we don't use, so use that and put it in some form that we can then get it back when we need it. You can do that with batteries, energy storage. That's what we think of when you think of it. And Elon Musk will build you a battery pack, a Tesla battery pack, that could keep a city running for 2 or 3 hours at huge expense. So that's one way. But there are other ways to store energy. It doesn't have to be in batteries. For example, we could store it in hydrogen. We already know how to make that. Use the hydrogen later to generate electricity. Here's a group just outside Toronto that are storing energy in air. They're storing it in air. So what it is, they're over top of an abandoned salt mine. And this mine has these huge underground chambers that are empty. So they pump air down there. And they just come pumping it in until it builds up to high pressure. And then when you need energy, you let that air come out through a little tiny orifice. And just like a balloon, you blow it up. When you let it go, go, pfft. Well, this air comes rushing out of that little hole, and it spins a turbine that generates electricity. Air, storing energy in air. You may have heard of the myth of Sisyphus. Poor Sisyphus. I'm not quite sure what he did. He insulted the gods. I don't know if he fooled around with one of the gods' wives or something, but he annoyed the gods. And his punishment was to roll a big stone up a hill every day. And it would take him all day at great effort to get this stone up the hill. And then once he got it to the top, the stone would roll all the way back down again. And he'd have to start over for the rest of his life. Sisyphus probably didn't know it, but he was the world's first mechanical battery. Mechanical battery. Because think about it. As he's putting muscle energy into that stone. And as the stone goes higher, it's gaining energy. It's gaining potential energy, the potential to fall. And when it does, when it releases that energy, that's a lot. So that's stored energy. Well, there's a group in Europe taking the idea of Sisyphus one step further. They're building a tower that has these cranes at the top that lift huge concrete blocks. And these blocks, by the way, are made of demolished buildings and industrial waste. They just stack them up in a big tower. And they're electric cranes that lift it up. So they do that when there's surplus energy. And when you need electricity back, if the lights go out or the wind isn't blowing, you pick up a block and you let it fall. Let gravity pull it down. But as it does, that motor at the top of the crane that lifted it becomes a generator, and it spins and makes electricity. Gravity. You're storing energy in gravity. And there's 5 cranes, so you can always keep one of them moving at all times. So there are lots of ways to store energy. Here's one more. This is a group in Norway. These big containers store heat, and they do it using sand. They do it using sand. It turns out that you can heat sand up to almost 1,000 degrees and it won't melt. You've probably had that experience where you go to the tropics on your tropical vacation, white sand beach, Mexico, you go out, you forget to put on your flip-flops. Hot. Sand is really, really hot. Here's the same thing in infrared. What they're doing is they're heating sand up, and it holds onto that heat. You just run pipes through it, and you can get that heat out. They're getting seasonal heat. Seasonal heat. It gets them through their dark winters. They're a northern country like we are. They're heating homes with sand. And they do it on a larger scale than this. They dig large pits, fill them with sand, heat it up, and it stays hot. That's amazing. So energy storage? Yeah, lots of innovative ways to do it. And this is what we need, our innovative thinkers. That's what we need coming out of these universities of ours, is innovative thinking. How else can we do this? How can we generate electricity? How can we store electricity? How can we use it more efficiently? Yeah, we can do that. We can do that. Just want to leave you with a couple of others here. Canada is investing in a new concept called small modular nuclear reactors. Now, these are much smaller than what we've been building in the past, like what's in Ontario at Darlington and Bruce and all of these multi-billion-dollar, multi-reactor things that can power a whole city. These are much smaller. They're the kind of thing that's been powering nuclear submarines and aircraft carriers and Russian icebreakers for decades. And they have a very good safety record. These things are completely self-contained. A colleague of mine at the CBC, he got a trip to the North Pole on one of our Canadian icebreakers. And they're all diesel powered. So they slammed and banged their way through ice. This was a number of years ago when there was still ice up north. And when they got to the North Pole, there was a Russian nuclear-powered icebreaker there waiting for them. And the Russian icebreakers are huge compared to ours. The Russian captain invited the Canadians over for dinner. So they all went over. And the Russian captain asked his Canadian counterpart, he said, so how many tons of diesel you burn getting here? And the Canadian captain calculated and told him how many tons of diesel he'd burned to get to the North Pole. And the Russian went, I think we burn a few grams of uranium. And he was right. Uranium is so dense. There's so much energy in that, even more than oil. And it doesn't have any carbon emissions. We've got to have intelligent conversations about this because these reactors are not like the old ones. They would be built in a factory, not on site, transported to the site and put underground. You don't touch them. Nobody touches them. They're underground. Nobody can get at them. And they can even melt down. If they have an overheat, they run out of fluid, they don't melt. They won't explode because they use a slightly different form of fuel. There's a number of different designs. And Canada's investing in this right now. In fact, they can even burn the waste, the nuclear waste that we now have on our sites. They can burn that and reduce the amount of waste that we have, including plutonium. So this is something we need to talk about. One of these could power a small town, which would be great in the north. We have all our communities that are currently running on diesel. So they could have one of these. So let's have some intelligent conversations about nuclear power. It's a social issue, it's an economic issue, and we have to really look at it very carefully. But it's 24/7. It's always there, so the lights will stay on. And then there's nuclear fusion, which is the opposite. What we're doing now is we're taking really big atoms and we're breaking them apart to get energy out. Fusion is you take really small ones and you bang them together. And they fuse, and you get energy out that way. The problem is, they don't want to do that. Like right here, if I try putting my fist through this podium, it doesn't work because the nuclear forces that are holding the atoms in my hand together are resisting the forces that are holding the podium together. Even though my hand and this podium are 99.9% empty space. The atom is mostly empty space, but it's the forces. So if you can force things together, that tremendous energy that's in the nucleus will be released and you can get it out. But you need to hit them hard. That means you got to make them very, very hot. And for these fusion reactors, it's almost ridiculous. They have to heat the fuel 150 million degrees. That's 10 times hotter than the center of the sun. 150 million degrees. What kind of container do you put that in? You can't let it touch anything. So the only way they can get the fusion to work is to suspend it using enormous magnets and form it into the shape of a donut so that it's in this donut-shaped room and doesn't touch the walls. And the problem so far has been the amount of energy to power those donuts is greater than the amount of energy we're getting out from fusion. So, but we're at a critical point right now. There's a big one being built in France. There's one being built in the States, a smaller one. And there's even a Canadian version being built in England right now that are getting smaller. So we're getting close. There's a joke in the fusion industry. Fusion has been 10 years away for 50 years. But watch, we'll see. We'll see. This is coming. It's coming. But again, emissions-free, you don't have all the radioactive waste, and once it's up and running, it'll run itself. It's like a little star, little piece of the sun. And it won't blow up, because if there's a power failure, the magnets die, and it just goes out like a light. So it's not, you can't get a meltdown. It just won't do that. The last thing I want to leave you with doesn't require all this high technology. In fact, it's very low technology. Right now, we're building communities, especially suburban communities, out of these little boxes. that have small windows on the south side. If you took the same materials that we're using to build houses today and just change the shape of the house so it's got big windows on the south side to let sunlight come in, a thick concrete floor that'll absorb that sunlight and store it, and then you just cleverly open and close vents at the top and the bottom, you create a natural circulation of heat during the wintertime, and you can even cool it in the summertime. You don't even need a furnace, just by changing the shape of a house using conventional. I've been in houses like this, and it's amazing. No high technology involved, just the shape of the house. So that means we got to change building codes. Are we going to do that? Would you be happy living in a house like that? When you saw your electricity bill being zero, I think you might. Although you'd still need some electricity for the lights, but that's about it. I also have a silly chapter called Great Idea, but about things that were great ideas but didn't work. One of them is space-based solar power, which has been around for a long time. So you put up this gigantic satellite in orbit, and it captures sunlight and converts it into either a microwave or a laser beam, and you beam it to the ground. And then on the ground, there's a big receiving station that converts the microwave or the laser into electricity. Of course, I don't know how we'd feel about having a laser beam coming down from space. Talk about a no-fly zone. I don't know what the migrating birds would think of that. Instant cooked chicken. Anyway, that's one idea. So we got all these crazy ideas. The technology is already there. We don't need to invent anything new. Why aren't we doing it? Well, besides the elephant in the room of the oil, we have social issues. But we got a great example of how we dealt with an invisible threat to humanity. An invisible threat to humanity. Over 2 years, we were faced with a virus that was killing people by the thousands. We were seeing them. Some of you may have relatives who were killed. Seniors are being killed by this virus. And we were told, this thing is deadly, it's spreading around the world. We've got to change our behavior. First of all, stay home. Don't go to work. Lock down. Wear a mask. Social distance. Wash your hands. And when we did that, during the very beginning of the COVID epidemic, when we stopped driving our cars, the air cleaned itself. This is China before and after, showing you carbon emissions coming out of China. The skies went clear. Carbon emissions dropped in a matter of days, and not just carbon dioxide, but nitrous oxide, sulfur dioxide, the things that are polluting our air, they dropped dramatically. And skies over cities that have been polluted for decades turned blue. And this wasn't just in India, it happened all over the world. Blue skies. And that's good news. That's good news. As soon as we stop dumping our garbage into the air immediately begins to clean itself, at least of the particulate matter, the stuff that can rain out. The carbon dioxide is going to stay for a while, but at least the air does start to clean itself if we just leave it alone. That was good news. Science stepped up to the plate. To their credit, the Chinese scientists, when they identified the virus, the source, they immediately did its genome, its genetic sequence. They sequenced the whole thing, and they just sent that out to the world. And there was this enormous international effort, including here in Canada, to identify that virus. How do those spikes work? And by the way, this wasn't the first time we saw one of these. This is related to another virus we had to deal with in 1991 called SARS. It hit our hospitals. It's the same family. So we already knew a bit about it. So the science stepped up, identified it. Industry stepped in and said, yeah, we can make vaccines by the billions if we knew. And number two, the government stepped in and said, we will support the science, and we will support those who lost their jobs if we need to, and we're going to put out the mandates on what to do. 3 elements. The fourth element, the public. We bought into it. We bought into it. We changed our behavior. Well, most of us did. My fiance lived in Ottawa during this whole thing, and she was right downtown, and she had to live with that noise. And she actually took her dog for a walk, and the dog pooped. She took the dog crap and threw it in one of the trucks. Anyway, they were a very small, highly vocal minority who put out misinformation about vaccines and freedom and all of that stuff. But they were most of us bought into it, and we did it. And we beat it. We beat that invisible threat to humanity. And what were we told? We were told we have to flatten the curve. Flatten the curve. We did. We're still dealing with it, but now we're all vaccinated, and look at us here in the room. Look at us here in the room. We couldn't do this 2 years ago. It's great. It's great. We beat it, this invisible threat to humanity. Well, here's another curve we need to flatten, and we haven't flattened it yet. And we haven't got all 4 elements together. The science is telling us, yeah, there's a problem. Industry is saying, we've got the solutions. And it turns out that the green economy is really fast growing. If you invest in it, like put it on your buildings and whatnot, you're saving energy because fuel prices are going up. If you're in the business, you're creating jobs and you're making money. So industry's into it. The government, well, this year's budget, federal budget, includes more money for alternative energy, but it's still not enough, but they're there. They're beginning to turn around. The public, there's still skepticism. There's still skepticism and fear. So let's get all 4 elements together and do with energy what we did with COVID. It was a great example, and we did that so fast, this invisible threat to humanity. And by the way, it's not a revolution. It's a new industrial evolution. I like to think of evolution rather than revolution. Because like I said before, when you have it polarized, good and bad, that's a conflict, and that's a revolution, and that's not good. Evolution is when you take what you have and you make it better. Think about your phone. Think about this. When I was a kid, the phone was on the wall, and all it did was talk, and you had to stand beside it to do that. Now look what it can do. Talking is probably the last thing you do on your phone. This didn't come from a big necessity. We didn't need better phones. It didn't come from a government mandate that said, you have to have a better phone. It was a good product. We bought it. We liked it. Okay, electric cars are great products. Try them out. That's how it happens. It evolves over time. It just works its way into our society. And that's the way these alternative energies are going to come along. But we got to move faster than we've been moving before. They're there. And the main reason that we have to do that is because of this. I met the guy who took this picture. Again, I'm very privileged as a journalist to meet amazing people. And the guy who took this picture, his name was Bill Anders, and he was on the very first mission to the moon. It's 1968. It was Apollo 8. They didn't land. They did back in 1968 what our Canadian astronaut Jeremy Hansen is going to do next year. They just went to the moon, they went around it, and then they came home. But they were the first humans to leave the Earth and go to another celestial body. And they were the first humans to see the Earth as a single ball. Those who go up today on the International Space Station, they don't see this. They're too close. They can see the curve of the Earth, but they can't see the whole thing at once. It was only those who went to the moon that did. And when I asked Bill Anders about taking this picture, I said, what was it like to do that? And he surprised me with his answer. He said, we weren't expecting to take that picture. Our job was to photograph the moon. We were to photograph the landing sites. So when they landed, they'd have good maps in their hand. And he said, it wasn't until our 3rd time around the moon when we just happened to be facing forward and the Earth came up above the horizon. And the commander said, did you get the picture, stupid? Yeah, click. Because they were all stunned by it. They were stunned by it. And this has become an iconic picture of ourselves as a single living unit. And what Bill also talked about was the contrast between that beautiful blue living Earth and the totally dead moon that's at the bottom. The dead moon that's at the bottom. If you go to the moon, you got to wear a spacesuit all the time. If you don't, you got about 15 seconds to live. Because there's no air there. It's a dead world. Do you want to see my imitation of a walk on the moon without a spacesuit? Okay. Let's suppose we're on the moon right now. And we're inside a building like this, so it's providing all our air and all our oxygen. We're happy, the pressure. And I want to go for a walk. And I just step out the door and I forget to put on my spacesuit. Here's what happens. That's one small step. You breathe out, but you don't breathe in because there's nothing out there. It's a vacuum. And as you're gasping for that breath, there's no air pressure around your body, so all the fluids in your body boil. They burst out of your eyeballs and your ears and your mouth and your nose. And it comes out and it makes pink snow. It falls to the ground slowly and low. You fall to the ground with it, gasping for a breath that will never come, lying in your own frozen snow, and you're getting cooked by cosmic and solar radiation. That's a walk on the moon. The moon will kill you. So will Mercury, Venus, Jupiter, Saturn, Uranus, Neptune, and even Pluto, which isn't even a planet anymore, they'll all kill you. We are looking for another one of these. We haven't found one yet. We're up to 5,000 planets going around other stars. They'll all kill you. If we do find another Earth, and we will, it's going to be really far away, and we can't get to it. We can barely get to the moon, for God's sake. So this is it. This is it. We live in the Garden of Eden. Yes, people will go to Mars, and they'll set up a colony there. But there's no oxygen on Mars. They'll have to wear spacesuits every time they go for a walk. They'll have to live underground. It'll be like moving to the South Pole. Sure, you can do it. But why are you leaving the Garden of Eden to go to a really cold, dry, awful place? Sure, it's neat, looks great. There's good skiing at the North Pole, by the way, on Mars. But this is it. This is it. So let's think about that, and let's move ahead. We've been thinking a lot about the problems for all these years. Let's start thinking about solutions. Let's take the model of COVID and get on with it and deal with it in a short time. I believe we can. I'm optimistic about the future, and that has been the biggest feedback that I've gotten from people who read my book is that, wow, finally, an optimistic look at the future. How refreshing. It's about time. So it'll be available in the back. I'll be signing it later. But thank you so much for inviting me to come here tonight. Thank you to McGill University. It's been a real honor. Thank you.
Thank you very much, Bob, for an insightful and information-rich presentation, for the hope that you're sharing with us, and also the good laugh. The ideas you bring forward could not come at a better time for us here in Montreal, where the recent ice storm sparked new conversations in all our families, in all our circles of friends around finding alternative green energy sources. I know there are many questions from near and far. We have over 200 people online, so nous vous saluons, bienvenue. So I would like to invite Bob and Dr. Joe Schwarcz to the center stage for the Q&A. And while Dr. Joe Schwarcz is joining Bob, I would like to introduce him. Dr. Schwarcz is the director of McGill University's Office of Science and Society, which has the mission of separating sense from nonsense. I love that mission. He is well known for his informative and entertaining public lectures on topics ranging from chemistry of food to the connection between the body and the mind. Professor Schwarcz has received numerous awards from teaching chemistry and for interpreting science for the public, and was the first non-American ever to win the American Chemical Society's prestigious Grady Stark Award for demystifying chemistry. Congratulations. He has also been awarded honorary degrees by Athabasca University, Cape Breton University, and University of Windsor, and Simon Fraser University. Dr. Schwarcz, Bob, the mic is yours.
Well, thank you. Bob, you mean the picture of the Earth was not a fake and it The moon landing was not staged in Texas on the back lot.
They really did it. I've met people who've been to the moon. They really did it. I believe them, yes. Why would they go to so much trouble to build a rocket that's capable of going to the moon and not go to the moon? Plus 400,000 people worked on that project.
And the Earth is not flat.
It looks flat.
It looks flat.
It measures flat.
And if you go to the Flat Earth Society's conference, you hear scientific-sounding gobbledygook about the Earth being flat.
So how come nobody's been to the edge yet?
Right. Oh, it's
Nobody's
big,
looked over the edge.
It's all these ice-covered mountains around.
Oh, right,
the
there's a
edge.
wall. Yeah.
There's a wall. Well, Bob, that was really a great talk. And one way to measure a great talk is, we've had questions submitted before, and you've answered just about every question that was submitted. So you really did a great job. But there are a few, and then after we will throw it open to you guys to ask questions. But one of the nice things about moderating something like this is that you can steal the spotlight and ask a question. Okay. The windmills, gigantic, as you said. But one thing that I've been reading is the lifetime of the arms, which is not that long, 20, 30 years they're talking about, is that these are so huge. The question is, what do you do with them after?
There's an emerging industry to recycle those arms. There's a group in Europe, and they take them and they cut them in half, and it's shaped like a crescent, if you think about a blade cross-section. And they're using them as bus shelters. Cutting them into sections, using them as bus shelters. So that's one thing. I was also thinking, they put me up in the hotel just across the street here on Sherbrooke, and I'm looking up over the mountain, and I noticed there's that big cross that you have on the hill that's been there for a long time. Imagine the arms of that cross rotating, generating. There must be fabulous winds out there. And I thought, if that was the case, people would go, that's really ugly. I don't like looking at that. But that's the kind of thing we got to think about. People don't like windmills because they think they're ugly.
I can tell you there are a lot of people here who would agree with converting that cross into a windmill.
That'd be a great spot.
A question that was asked by several people. How did you first get interested in science?
I grew up in the space age. I grew up in the small town of Orillia, just north of Toronto. And I remember Sputnik, the very first satellite, and how everybody was both excited but terrified that the Russians had put up this thing that could go all the way around the Earth. And if they could put up a satellite, they could put up a nuclear weapon, and they could drop it anywhere, including over our heads. And a couple of things happened. First of all, I got right into it. I thought, that's fabulous. This space, how neat. My mother came home with a book from the grocery store that was simply called The Planets. I still have it. It's a golden book of knowledge, library of knowledge. It's a full-color, thin book, and it's got drawings of all the planets. This is 1957. And it was actually a Russian artist who did it. But I completely fell into this book because it was quite realistic. And I discovered that Saturn's got rings around it, that Jupiter has this big storm that's bigger than the Earth, and that the Earth is just one of a whole family of planets, and it was amazing to realize that as a kid. And then I just followed the whole moon missions. I knew the names of all the astronauts. I watched them land, not just the first mission, but all of them. And it has been an exquisite pleasure to become a journalist during the time when we sent robots out to all the planets. And I made it a mission of my own to be at mission control where they get the pictures from these robots, usually in California, when we went there for the first time. So I got to explore the solar system, and I've since met people who've walked on the moon. So it was the space age that got me interested in science. And during that time, sorry about the long answer, but during that time, the education system realized that if North America is going to catch up to those evil Russians, we need an educated society. And they changed the school curriculum, and science was brought to the front, science and math. We had new math. You remember that term? New math. That seems to have faded away Science is not as popular as it was. So those were the things that got me into it, and I still love it. I still love it.
So Sputnik started it all.
Sputnik started it all.
Thank the Russians.
Yeah, thanks to the Russians.
Okay. Again, a question that came up from several people is you talked about all the technologies, industrial technologies. What can the average person do? Taking sponge baths instead of a shower, bicycling to work, these things.
All of that, all of that. Again, it's multifaceted, and it's not just the technology, it's behavior. So in the same way that we changed our behavior for COVID, the way we moved around, we can design our cities to have better public transit, better than what Montreal's feeling tonight, but more public transit, make it safe, make it fast, make it convenient. If you have a house that has a roof that faces south and you get lots of sunlight, think about solar panels. Just think about it. Investigate it. Find out what they really cost and how long it takes to get those costs back in the savings on your fuel. It's not for everybody. Depends on where you live. Put a heat pump in your house if you own a house. Cut down on your fuel bills that way. So it's everyday things. And then talk to your politicians. Vote smart. Vote for politicians that support that. Tell your kids about it. Tell your kids about it. Both about green technology, but also about the green earth. Take your kids or your grandkids or anybody you know who's about that high and rip the device out of their hands. Tear them away from their computer games. Tear them out of the arms of their overprotective parents and take them to the forest and shove their face in the dirt. Turn over some rocks, see what's going on underneath, and you know, let them appreciate this beautiful world that we live in, because that's what we're trying to protect.
I'll try that with my grandchildren.
Go for it.
See what my daughter says about that.
Go for it. Don't tell your daughter, just do it.
Obviously, there's consensus in the scientific community about climate change and that humans are a big part of it. But consensus doesn't mean that there are not outliers out there, right? I mean, we're just like in so many other areas of life, we're talking about the bell curve. And there are the outliers who, of course, have all kinds of other ideas about climate change. And some of them are scientists. And one argument that comes up often is that it is really water vapor in the atmosphere that is driving the climate change, and that carbon dioxide emissions are a trivial contributor.
There's no question, there's more water vapor in the air than there is carbon dioxide. The thing is, the Earth's water balance hasn't changed almost since we've been a planet. This dihydrous monoxide, that's in this
Dihydrogen monoxide.
Oh, you're changing me again. Dihydrogen monoxide. This stuff. This is the same water the Earth has always had. It gets recycled through the water cycle. So it's been through a dinosaur. Would you like a drink? No, it is. It's true. So the water vapor's always been there. The water vapor's always been there. It comes and it goes. As climate changes, you get more or less water vapor in the air, and sure, that can cause cycles. But it's the carbon dioxide, we're adding to it. We're adding to it, and the indications of that are clear. We have clear data gathered from scientific instruments on the ground, in aircraft, and in space that are watching it go up. We even know where the sources are. So that's the difference. The water vapor's always been there. It is a component. But the carbon dioxide, we put our foot on the accelerator. All of those other natural cycles that the Earth goes through, the ice ages that I was talking about before, those are natural cycles. We know about those. We know about those. It's the carbon dioxide, our industrial, the last 150, 180 years, is on top of all those natural cycles, and that's the difference.
Agriculture is very often talked about as a huge contributor to climate change.
Yeah, cow farts.
And cow farts, yeah. How important is it really?
Well, I mean, a meat diet does take up a lot more land because you've got to grow the corn to feed to the cattle. Then the cattle need land or whatever you're feeding to them. So it's more energy intensive, no question. Some of the fertilizers that we're putting on the ground release emissions. The cows themselves, when they burp and they fart, they release methane. But we've always had big animals on the earth, so I don't like blaming the cows. Our prairies were covered in millions of bison and buffalo for a long time. So there aren't as many cattle now as there were then. So I don't want to blame the cows. But we can't think about the agricultural industry just like we think of every other industry. Think about all of them. How can you cut down on your emissions? How can you cut down on your energy use? And do it in sensible ways. And I think not just agriculture, but everybody.
Yeah, another industry that is being targeted is the plastics industry. Now, of course, we hear a lot about plastics, about nano plastics being in our water, in the air, and about the great garbage patch in the middle of the Pacific Ocean. But the production of plastics is a very energy-intensive industry.
Yes, it is. And plastics themselves, we just did a story last week on Schwarcz about the garbage patch that you just mentioned that's out in the Pacific now has life on it. It's its own ecosystem. And these are creatures that would normally be on shore. They're not used to being out in the middle of the ocean, but they're using the plastic as rafts to live on it. So there's a whole new ecosystem out there. It's an invasive species in the middle of the ocean that we introduced with our plastic. So plastic waste, yeah, we got to really take care of that. The beauty of plastic is that it can be recycled. It can be recycled. Although, when you start with a high quality product, when you recycle it, it gets lower quality. So you go from, like, I don't know, the dashboard of a car to a garbage bag, and then eventually you can't recycle that. So how do we use it? What else can we package it? Certainly. I don't think we're ever going to get rid of plastic because it is convenient in many cases. So if we can, cut down on the one-time use, that's the big thing. We get away from the one-time use. Let's do that. That's a start.
And I think it is a very good start, and I think that a lot of people are buying into that. And the straw up the nose of the turtle has had a huge impact. That single picture in National Geographic has really made people think of...
I've also thought about aliens coming to Earth in several million years from now when humanity's gone, if we're gone, and they come and they see this planet, and they're trying to figure out what's going on. There'll still be lots of life, just there won't be any people. And if they dig down, they'll find this miraculous material underground, and it'll be like a precious metal to them. Precious metals, gold and silver and all these things, the beauty of them is that you can melt them down, and they're still gold. You can melt and reharden gold as many times as you like. It's still gold. That's why they're precious metals. So they'll find this magic stuff called plastic. And they'll think, wow, look at this stuff. You can form it into any shape you like. There'll be plastic jewelry worn by aliens. That's just my thought.
One argument we hear often in the debate between the so-called climate change deniers and scientists is... The scientific argument is, look, 97% of all scientists agree that this is, real and it's man-made. Where does that 97% business come from? And is that reliable? Yeah,
that's like people who say we only use 10% of our brain. There's a 90% chance they're wrong. That consensus in the scientific community comes out of the IPCC, the Intergovernmental Panel on Climate Change. And the way that came about is really interesting. The United Nations went to the scientific community and said, okay, we have two questions. One, is climate change real? And two, are humans responsible for it? Or how much are we responsible? And what the IPCC did was they collected scientists from 50 different regions around the world, representing the entire globe. And their job was to not do new research, but to gather together research on the climate that's already been published, that they knew about. And then they gathered this world body of knowledge, and they put it together into a report that was then sent out for peer review. So the scientific data has now been peer reviewed twice, and then that's what they put out to the world. And the answer was overwhelmingly yes to both questions. Climate change is real, and humans are responsible for it. Now, it was a bell curve. There were the extreme pessimists who said, no, it's worse than you say. And there were the optimists that said, no, it's not as bad. And that depends on the projections, where it's going from here. Are we going to level that curve? Are we going to flatten that curve or not? So that's where the uncertainty comes from. But that's where this majority of people come from. So there are always going to be outliers. And I don't have too much problem with that, because sometimes they'll raise issues that we need to look at, or non-issues, and say, no, that's not, we've already covered that. So that's part of the process. But science works on data. Science, it's not by consensus. It's on the hard data. And the hard data is being gathered every day on so many different fronts. So that's what I believe. I believe the IPCC. I believe Environment Canada. I believe the National Oceanic and Atmospheric Administration in the States. I believe East Anglia in England. These organizations that just focus on the climate, I believe they know what they're talking about.
Well, this leads us to something you addressed partially, is how do we battle the misinformation? It's a very tough battle because, as we were discussing, the misinformants are very good at what they do.
Yeah. This is a challenge that I think our universities are facing right now, is how to educate young people on knowing the difference between the truth and non-truth. We're living in an age of misinformation. You're exactly right. And it's a strategy that worries me. People are putting out lies. They're putting out misinformation, and they know it's wrong, but if they just keep saying it, if it suits their purpose, keep saying it long enough, you get it out in the public mind. And that's the idea, just get the idea out there. So it's up to our academic institutions to communicate science in the way that you do, to say, here's the truth. Like I said at the very beginning of my talk, science is one of the last institutions we have that looks for the truth. And that's what we do. We got to get that truth out there. You can't battle them. You can't battle the deniers. You've just got to stand strong, because they'll put you on the defensive. And if you're on the defensive, you're not strong. You just got to stand strong. This is what I believe, and here's why I believe it. And let the truth prevail.
Well, we're on the way. Tucker Carlson got fired today.
Tucker Carlson got fired. Exactly. So if our institutions and the science graduates, if they don't have to become scientists, but if they use their scientific training to make decisions, because we've got some hard decisions to make right now with climate change and energy and all these things, but it needs an intelligent conversation. So we need a scientifically literate society to do that, and I believe we can.
So you've been in this for 40 odd years.
Actually, it's 50 now.
50 years.
Yeah.
All right. So in
Sure.
the
1972, I started at the Science Center.
in the next 50 years that you'll be in this, what do you think are going to be the biggest breakthroughs that reasonably can be expected?
Wow. Well, there are amazing breakthroughs happening in genetics. That's my weakest subject, so I can't elaborate on that, but I do know that by understanding the genes of living organisms, including ourselves, it's leading to so many other things. We're discovering that a lot of our evolutionary history is being rewritten because we're seeing the genetic pathways that led to us or led to whatever's out there. So I think there's going to be enormous advances in medicine and in genetics. We're going to discover the universe, more of it. Do you know that 95% of the universe is made either of dark matter or dark energy? And when a scientist says dark, that's scientific lingo for, I don't know, 95% of the universe is made of that stuff, and we don't know what it is. We're beginning to map where it is, but we still don't know what the heck it is. So our ignorance is still greater than our knowledge. So we're going to discover the invisible universe. And I hope that 50 years from now, we'll be looking back on this time, and people will go to museums, automotive museums, energy museums, and they'll see these vehicles that, you know, the curator will start it up and it'll go, people rode in those things? You know, there's smoke coming out the back and the engine clattering away up in the front. That's not like my electric car. I think they'll look back on this time and think, wow, what a remarkable time, but I'm sure glad we left that behind.
Do you think we'll really replace all gasoline-powered cars by electric by 2030 or whatever the target is?
No. There's too many, and they're too ingrained in our culture. It's going to be a gradual evolution, but they will work in. They will work in just like the phone did. I know in the U.S. they're mandating 2/3 of all new cars have to be electric by 2035, I think, something like that. So yeah, the manufacturers are getting into it. All the manufacturers are coming out with electric cars now. So the price is going to come down because they get it.
We're going to have the issue of what to do with the old gasoline-powered cars.
Put them in museums.
Billions of cars.
Yep.
Yeah.
Recycle the metal. Recycle.
recycle.
But the government's going to have to step up to the plate for charging stations, to put in infrastructure, that kind of thing. So the government can be a part of it for infrastructure to help companies that are starting up, tax breaks, whatnot.
Okay,
But it's coming.
we're getting signal that we're short on time, but maybe
Yeah.
we can take a couple of questions from the audience. There is microphone there. There's a microphone there on either side.
Oh, question here. Yes, sir.
Yeah.
Of the Climategate scandal 2008, it was to show that actually the misinformation can come from both sides, and it often does. People who are well-meaning often also have interest in, advancing their careers. It was a disaster. It really set back the, the climatological environment. Even the American Physical Society pulled its acknowledgement of, addressing the role of climate change in the evolution of the global ecosystem. I'd like you to comment on that and suggest how we can propose mechanisms to prevent that from happening in the future. The other question I have regards the suggestion of nuclear fusion. To the best of my knowledge, in Europe we have ITER, which is already in operation. Certainly has not reached ignition, but certainly we have in New Mexico we have a national ignition facility, and 10 years too late. It'll take an extra decade. It always takes a little bit longer, but I believe last year they achieved ignition finally. How soon do you think we will achieve a stage where nuclear fusion will play a significant role in meeting the world's electricity demands? Thank you.
Thank you. I have a question for you, though, before you go.
Yes,
before
yes,
I
certainly.
address the fusion issue. What is the misinformation you're referring to with regards to climate change?
With ClimateGate in 2008, what we had was a very, very deep solar minima. And as a result, there were a lot of questions that were posed regarding the validity of the global warming hypothesis. Ultimately, there were some very clever devil's advocates who delved into the data and found that some of the data that was used for the analyses was actually falsified.
In other words, you're using information from 2008. The sun goes through natural minimums all the time. It goes through a cycle every 11 years.
11 years.
It has sunspot cycles. It has these solar minimums and maximums. It's always done that. Nonetheless, regardless of what anybody said back in 2008, our emissions are still up. The global temperature is still up. Oceans are still warming. These are all measurable data. These are all measurable data. So I'm questioning what you're using as data to deny that.
I'm not denying anything. I'm just questioning the role.
Using old data.
No,
2008.
climate scientists had taken data from the 1990s and early 2000s, and unfortunately, this does not question the role of global warming. It questions the scientific method. They had actually falsified the data in order to make their their analysis seem more convincing. This discredited the entire global warming hypothesis, which was unfair to both the global.
I'm not quite sure what you're referring to as a single event, but let me get on to the fusion. We can talk about this later.
Certainly.
Because I don't want to do it here. Fusion is going to be one element. The ITER project that you mentioned in France is a mega project that's been underway. It's an international project that's been underway for decades, and they haven't reached ignition yet. It's a demonstration. It's not a power plant. It's to demonstrate how to make a plasma produce fusion. It won't generate a watt of electricity. That's not its purpose. It's a research reactor. Massachusetts Institute of Technology has a smaller one called SPARC. It's in my book. The magnet technology has improved so that they're smaller now, and they can do fusion in a smaller space. They're talking 300 megawatts, the same as the small modular nuclear reactors I was talking about. So we'll have fusion reactors, we'll have nuclear reactors in small spots here and there to fill out remote communities, and they will be part of the montage of the wind and the solar and the tidal. It'll be regional, and they'll be part of a larger picture. It's not a magic bullet. There is no magic bullet that's going to replace oil. We're going to have a whole bunch of things. So let's get used to that.
Okay, we'll take
Thank
another
you.
one.
Okay, thank you.
Question, not a speech. We'll go to this side. No?
Hi there. Yes, thank you for the talk. I spoke with Tony Keller recently, who writes for the Globe and Mail, and asked him, what's the secret to a good question? And he said, make it really short, and then that way the person can interpret it however they want. So my simple question to you is, what advice do you have for the future scientists or the current generation who might be a student right now? That's it.
I didn't.
I missed you.
Yeah,
Sorry.
Okay, maybe it was a little too short. We can say it again. Very simply, just what advice, I guess, do you have for students or the young scientists, the next generation, in approaching the climate crisis, I guess?
Oh, what advice do I have for students in dealing with the climate
Young
crisis?
people, young scientists, yeah.
Okay. Well, first of all, don't be discouraged. Okay? I know it's scary, but if we all get discouraged, we stick our hands in the sand or we go get drunk and nothing happens. So let's not do that, okay? Let's just keep progressing and believe that there is a solution, because the solution's out there. It's just
sound
a matter
like my
of getting
dad.
to it. But it's not just technological, it's social, it's political, it's economic, in some cases even religious. So we have to have intelligent conversations about it and move ahead, get beyond the talk and move forward. So as a student, first of all, learn about it. Learn all you can about it, whatever you're interested in, and then try to spread that knowledge as far as you can within your circle. That would be amazing. If all the science students here did that, that would be amazing.
We have
Thank you.
several courses here at McGill that deal exactly with that.
But thank you for that.
Thank you.
Okay, we'll go over here.
You've spoken about incredible solutions and optimism, so thank you. But nothing has been, or you didn't raise anything about trees and oxygenation and those opportunities that nature provides. What is the most important thing? Are trees really important?
I'm glad you asked that. And I also talk about that in the book. There's a lot I left out that's in the book that I didn't talk about, including biofuels. Trees are important. We need to rewild our country. But it goes beyond just making conservation areas larger and more of them. But we can also rewild our cities. I have a slide that I didn't show tonight that shows an overhead view of a downtown city. And you see all these houses. And the rooftops are all white hot because we put black asphalt on the roofs and they absorb heat. But down the middle of the streets are all these purple dots, and those are trees. Trees cool. Trees provide natural air conditioning. They give off moisture. They absorb carbon dioxide. So yes, trees are natural carbon sinks, and they can also help to get rid of heat islands that cities produce. So the more plants, the better, but that's not enough. That's not enough. With our population growing and our cities growing, we're taking over wildlands. But that, again, is another issue, population. How do we control that? That gets messy. But you're absolutely right. You're absolutely right. We do need more wilding, including leaving the oceans alone, because they actually absorb most of the carbon dioxide.
Everything gets more and more messy the deeper you look into it.
Yeah.
Right? I just came across by coincidence today a study about pipelines and thousands of miles of pipelines around the world. And they have to clear-cut forests because you have to have a certain distance, right? And this is apparently a big deal in terms of the number of trees that have been lost by
Yes,
that.
and then there's the leaks coming from the pipelines that pollute the environment. I want to leave you with one final statistic that scared me, that I found towards the end of my book. During the 2 years of COVID, the most intense parts of it, they estimate that worldwide about 5.5 million people died from COVID. That's terrible. That's one of our major cities that died. The other statistic that I found, and this is from 3 independent studies, every year, between 7 and 8 million people die from the effects of burning fossil fuels, mostly from air pollution. But 7 to 8 million people a year. So twice as many people, more than twice as many people died from fossil fuels than died from COVID. That's wrong. And we've been doing this for 150 years. So this is nuts, okay? Let's let our current way of burning fossil fuels, that industrial age has come to an end. Let's enter a new green industrial age and move ahead. Thank you.
Well, I've gotten the signal that we are out of time, but of course we have to end on dihydrogen monoxide, right? And as long as people will sign petitions to ban dihydrogen monoxide, we have a problem.
Yeah.
And unfortunately, that happens. So what we need is scientific education.
Absolutely.
That's the key. Thanks, Bob.
Thank you, Jeff.
Great. And thank you all.
Thank you for coming.
And Bob will be out there signing the book.
Thank you very much once again, Bob, for offering such a positive and accessible perspective on the climate crisis. And thanks to you, Dr. Schwarcz, for leading such a great discussion. We really appreciate your presence here tonight. And on behalf of all our partners, McGill's Office for Science and Society, the McGill Office of Sustainability, the James Bookstore, the Faculty of Science, the Trottier Institute for Sustainability in Engineering and Design, here are small tokens of appreciation to both of you. And to all of you online and here on the McGill campus, thank you so much for joining us for this year's Mossman Lecture. And I now invite you to join me in the arts lobby for the meet and greet and book signing. Thank you very much and have a good evening.